right, good afternoon. Any questions? No questions? Yes? Quiz, question 8. Okay, give me a sec. All right, so the question says, if node J is to be removed, this thing here is J, which node should be copied in its location? And the rule says what? It's the smallest node in the right subtree. The smallest node in the right subtree is this one here, and so it should be L. Is that what the answer says? So we'll go over it in a minute, but that's how removal works. So if you have a a node with that has a right child, then you take the next smallest element and you move it up there. Yeah? What? Well, it doesn't. Okay, now that's a good question. Whether it would be better to, you have the choice. You could also take the largest element of the left subtree, but any one implementation is going to make one choice. So there's no great use in optimizing which of the two would be better. Really, what we want to achieve is we want to have a tree that's more balanced. And neither of those two will guarantee that in the end. You're going to see in 146 a bunch of binary tree structures that do a better job balancing themselves after insertions and removals. And so that's a more profitable way of optimizing that. Other questions? There was a hand up here somewhere.
There was part of your quote that said that if the node is removed, then the child of that node is then copied over into the place of the removed node.
Yeah?
The child of J.
No. It is the smallest child, or the smallest descendant, it should say. It has to be the smallest descendant because otherwise it's not a binary search tree. But if you find in the book where I said it wrong, send me an email, and then I will put it on the errata list. I would like to fix that if that's the case. And then you'll see your name in pixels on the errata list. Other questions? Yes? 15C final, sure. Oh yes, so it's the iterator. We seem to be doing a lot of iterators. So let me get some paper out. This is for a binary search tree, yeah. So if you have some binary search tree, and I'll just make an example of one here. And now you want to iterate over the contents here. So an iterator would want to visit first the 2, and then the 5, and so on. And so it's easy to know where the iterator should start. It should start with the smallest element. And you get the smallest element of any binary search tree by going left, left, until you can't go anymore. So you would start out at that position with a 2. And then, so the iterator would have a pointer to a node, and so when you call next on it, it would yield the 2. Now the trouble is, what is it going to yield next? If this tree was of the type where you had links to the parent, now which is certainly an option, some trees have that, then the iterator would have a simple life. It would say, well, I'm at a dead end, I'm going to go to my parent next. But we don't have that. So we have no link to the parent, and so how does the iterator find where to go next? Well, what the iterator can do is it can remember the path to the current node. And if you think about it, that's really a stack, because when the iterator started out at the node 10, it could say, well, I'm going to remember the 10 because I may have to go back to it. So, of course, it doesn't remember the 10. What it actually remembers is it remembers a reference to the 10, right? So if the stack really would remember a reference to the node, but I'll write it with the numbers to make it less messy. So then the iterator would remember the 5, which really means a reference to the 5. And I don't know, this is now an implementation detail that you need to work out. Do you push the 2 on the stack or don't you? You might instantly recognize it's a leaf, so you don't push it on the stack, but maybe you do. So let's say you push the 2 on the stack, and then you try to go further, and then you can't. And at this point in the call to next, you would then pop the 2 and yield it. And now you would have to have some decision process that tells you what to do with the 5. And do I give you any tantalizing details? I said, deliver the top of the stack as the visited node, but first push the left nodes in its right subtree. So I'm telling you everything. So, we have this on the stack. Now we're going to deliver the 2 eventually, but first we're going to push the left nodes in its right subtree. The right subtree is here, so it says now we're supposed to push the 7 and the 6. So this is the right subtree, and you push again the 7 and the 6 as you go along the left fringe of the right subtree. Now in the next iteration, I guess you would now deliver the 6, and now there is no right subtree to push because the right subtree is null, so you wouldn't do anything else. In the next step, it looks like you would push this, you would deliver the 7, and now you're supposed to push the leftmost fringe of the right subtree, that's the 8. In the next step, you deliver the 8, and you push the right subtree, there is none. Then we are all the way at the 5. Didn't we already deliver the 5? Tell me we did. Okay, work with me here. At one point we delivered the 5. I forgot to write it down. Now we're going to deliver the 10 and push the right subtree that is, where is it? It's these ones here. So we'll push, now my thing gets crazily messy, 20, 15, 13, and so on. So the key here is to follow the description, which accurately says what you should do. So in the constructor, you push the left fringe of the big tree, starting from the root, until you reach null, and that's all you do in the constructor. In the next method, you go exactly through the setup where you pop off the top, and that's what you're going to deliver. but before delivering it, you visit the right subtree and push its left fringe. So, questions about this, or does that sound like it's implementable? Any other questions? Okay, then I have a couple of things that I wanted to say about the exam that may or may not have relevance to the final. So let me So the first one was with a ring. So let's see. So I got the task to execute this thing here. So I'm making a ring with 3 elements. Benefit from graph paper. So let's see, what's a ring? A ring has a node. And the node is called start. And now I'm getting 3 of them. And this one I do remember. That they get set up in the circular way. And then the previous ones go the other direction. And at this point, it doesn't much matter which one is the first one because it is a circle, so might as well do it here. So that is the hookup after the constructor happens. That's how a ring with 3 nodes was done. Notice, by the way, that when I draw these arrows, I'm very careful that I have these arrows coming out of these boxes. I've had a good number of people choose a different style of drawing that didn't really work at all. So there were a bunch of people, who did this. So ring, I guess something like this. And then like this. Some people even drew like the little boxes inside here, but they didn't hook them up to the arrows. And the problem with that style is that when you now need to trace down like fiddly things like next dot previous equals previous or some such thing, it becomes essentially impossible to figure this out from the diagram. So if you don't know which of these arrows is next and which of these arrows is previous, then you might as well not draw the arrows. So this is fine for general intuition, but it's not good enough to actually trace code. So if you want to trace code, you really have to label everything. And so the style in the book is maybe ponderous, but it really gives everyone all the information that they want. So make sure that whatever arrows you draw, that they start out from the middle of the box and end up where they should. All right, now moving along. So now we have ring.set of Kim. So what does .set do? .set says, there's a bunch of stuff here for dealing with the old value that we don't care about. But the interesting line is start.data equals new value. So start, oops, now I forgot to put in the data, that wasn't good. No, I'm going to cram this in data. Sorry about that. Kim. Then here we have data, and here we have data. So now the next line says, where is it? It says ring.forward. So dot forward says start equals start.next. So now start points here. And now the next data is Emma. And then over here, then it happens again, start equals start.next. So now start points to the next one that's here. And over here it says Barbara. Sorry about the sloppy drawing. So this is how it looks like at the point that we're supposed to be doing something. And so now we're supposed to call ring.remove and analyze what remove does. Now when you look at the ring, you notice that the start position points to the last thing that was inserted. So I inserted 3 elements, Kim, Emma, and Barbara, and the start points to the node that says Barbara. So I spent a long time grading 160 or so of these rings, and about 2/3 of them did not have this feature. And about 2/3 of them start pointed to the first element and not to the last one. About 1/3 of them start pointed to the last one. And I think it's fair to say that just about everyone who got that part right also got the rest right. So just about everyone who knew where start pointed knew enough about how links worked that they completed the entire thing with the full number of points. The opposite was not true. There was a good number of people who was able to trace it through anyway and who just lost this 1 point. But there was also a good number of people who then produced little of any value. So that was interesting. So now the rest of it is of course pretty easy. So now we need to follow these steps here. So it says start.previous.next equals start.next. And so the way I graded it is no matter what diagram you deliver to me, I took that diagram and then I went, and I can now do this in my sleep, I went start, and then I looked up previous, and then I looked at the next field, and from here, I saw some arrows emerging with a 1 on it, then that was good news. So now, of course, they have to go to the next thing. So start.previous.next is start.next, so they have to go here. And then it said start.next.previous, and I will never forget this ever again. Start.next.previous equals start.previous, right? So start.next.previous, that's this one here, has to go to start.previous, that's this one here. And so that would be the number 2. And then it said start equals start.next. And yes, so that means that we are going to this one now. And that would be number 3. Okay, now we have a ring with only 2 elements, and Barbara is out of the picture. So that's how to do it, and that's the notation that I was looking for. With these things, it's easiest if you just follow this notation. There were some people who made 2 diagrams, which is fine, but it's more time consuming. There were a few people whose name I can now remember in an unfavorable context, who gave me 2 diagrams, but then they completely changed the layout in the second diagram, and I had to spend several minutes trying to figure out what exactly was what, because I could no longer use any spatial reasoning. Don't do that. So that was this question that I wanted to talk about briefly. So the interesting thing here is that you really do want to trace through these. The second question was the one with the debugger. And so let's see if I can still set this up. All right, so you have this class test 3 here. And so the simple question I had is, and why does the unit test fail? Well, let's find out why the unit test fails. Let's run it. And so we notice that the unit test fails in line 22. So it fails in this line, and it fails with a no such element exception. So that's interesting to note. Now, I got a whole bunch of explanations here that said the unit test failed because it was trying to ascertain that whatever. Now remember, a unit test is not a sentient being. A unit test does not try to ascertain anything. A unit test steps through one thing after another until something goes either right or wrong. It's just a piece of code. So the answer that you have to give is something that says the unit test failed because it encountered a no such element exception in this line here, in line 166 of the linked list class. That's why it failed. Okay, it did not fail because it had a bad day, or it was unhappy, or it was trying to ascertain something that it was unable to do. Right? It failed because an exception was thrown in line 166 of this code. So then, of course, it would be entirely fair and reasonable to say, how come it got a null in here when we didn't expect that null? And so that's where a bit of explanation would be awfully nice. So that's what I was kind of hoping for here. And so you can look at the solution to see how that null got in there in the first place. So those are the two things I wanted to say about the midterm. On the final, it's going to be a little different. I've posted a study list that you can go through. The final is not going to have anything on paper that is graded. I may collect your work paper in case it helps me, but you're not going to get any credit for anything that's on paper. It's all coding. You have 2 hours and 15 minutes, I believe, on the final, and so there's plenty of time for you to do whatever coding you need to do. Yes?
Do you have any questions here, Billy?
More or less.
Yes. No, there'll be, how many do we have this time? We had 5 questions with some A, B's, and C's. There'll be 8 questions without A's or B's or C's. There'll be 8 straight questions, no A's, B's, and C's. None of the questions involves more than, I believe, 10 lines of code. So if you can write 80 lines of code in 2 hours and 15 minutes, you should be fine. One of the questions, like I said, involves a short shell script. So make sure that if you want to get the points for that you get the credit for that. The other thing that I want to say is when you do those questions, there is a high reward for actually getting one done. it is very, very difficult to give partial credit in these exams. And so you really want to make sure that that you finish what you can. But on the other hand, don't go down a rat hole. I've sometimes seen students, who were working on problem 1, and it didn't work, and then it still didn't work, and then it still didn't work. But they were so close, and by the end of the exam, they got it done, but then they didn't get to any others. So you do need to budget your time as well. So what I would suggest is, you know your programming ability better than anyone else. When you look at the exam, you eyeball it, ask yourself, how many of these questions can you reasonably do? You don't need to do them all if you don't want to get an A. You can perfectly well get, in all likelihood, judging by the first 2 exams, if you get 4 of them done, you'll easily get a C and you might get a B. And so figure it out and make sure that you get those done first and then move on to the others when you have time. But try reasonably to get them done. That way you will maximize the points. So if you use the basic correct strategy and you pass the test cases, chances are you got it right, and then you can move on. So that also means that for preparing for the exam, there's, as much as I think it's a wonderful textbook and you should read it many, many times, that's probably not the winning strategy for doing better on the exam. The winning strategy is to do more problems. So if there are any problems that in the past that you felt you didn't really understand why they worked, just do them again from scratch. Without looking at anything, just start afresh, and that way, you get more coding practice. I gave you a list of problems from the textbook that you can work through, and that are somewhat related to the exam questions. So of course they're not going to be the exact same things as the exam questions, but they are related, and so they should give you valuable information as well. So if you do all of that, and I realize you have other finals than just this one, that should be the best that you can reasonably do. There was a question somewhere here about the exam. Yes?
Are they going to be like the previous midterms where they're based off homework questions?
They're going to be more or less based off homework questions, but not quite as much as the last midterm. The last midterm was extremely based on homework questions, but there's one that's based off a previous exam question, but there's a couple that are somewhat based on homework questions, but not to the degree that you had before. I will provide unit tests, yes. For 2 reasons. One is so that in case you find the problem explained, that the unit test should help you understand the problem. And also, I realize that that's hard enough to do the coding. If you also had to supply the test cases in those 2 hours and 15 minutes, that would be good. But so I will supply some way of testing each and every one of the problems, yes. Yes?
Are you going to curve the overall grade?
I'm not going to curve the overall grade, but I will curve the grade of the final. And now then the overall grade is a sum of curved grades, so it's also curved by construction. So I will do the same thing with the final as I did for the midterms. I'm going to drop, and then I'm going to curve. Yes. That may not be, before you get excited, that may not be in your favor because a lot of people, did pretty well in the homework, so the curving there is probably less of an advantage as on the exams. The exams by construction are so as to give me information about that allows me to separate the A's and the B's, and so those are definitely curved. That reminds me of one other thing that I wanted to briefly mention. So a while ago, there's a computer science professor's mailing list, and there was this discussion on exams. And so everyone was complaining that students came into their classes and said, how come I got 90% and I didn't get an A? And that perception usually shifted by the end of CS1 when someone said, how come I got 70% and I got an A? And so I think the consensus that everyone came up with in the end is that there's kind of 2 kinds of exams. That, there's like a driver's license exam where you've got to pass the exam and otherwise you're not allowed to drive. And then there is a feel-good exam where where you get 90 or 80% and the illusion of knowledge, but it doesn't actually matter whether you learn anything or not. And so the latter, happens a lot in courses where that are not really required later. But computer science is definitely like the driver's license exam. So the whole reason why we're forcing you into this degree of suffering in CS1 and CS2 is that in CS3 that you can code. And that I will never again hear from a CS3 instructor, how come they had 2 semesters of computer science and they still can't code a simple loop? So you will need to demonstrate that you can code in the final. And so don't be depressed if some of the problems are hard. Those are there to separate the A's from the B's. Do the ones that are reasonable to you. And, I think these exams, having taught these courses for many years, do, as unpleasant as they may be, they do capture reliably where people are, on the scale of knowledge. If you disagree, feel free to let me know. All right, on to the lecture. Oh yeah, a fun fact of the day. If you go to the New York Times and look at how hard is New York's algebra exam. So they have an algebra exam that I think people in 9th grade have to take, where it says, questions such as this one. So this fellow has $50 in a savings jar and is putting $5 every week. This one has $10 and putting $15 every week. And then they have 4 choices here about the graph, and you should pick the right one. Or over here, there's a graph of a function with 3 zeros, and they're supposed to, you can see there's a 0 at 1, 1 at -2, and 1 at -4. And they're supposed to figure out which of these polynomials it is. And so, of course, the New York Times readers, they all say, oh my God, I could never possibly pass this exam. But the reason that they give this exam in 9th grade is if you can't pass this exam in 9th grade, good luck if you ever want to go into computer science. Right? I mean, these are kind of pretty basic things that, polynomials or, simple graphs when about linear curves or, rates, something with selling large and small candles. I mean, this is not exactly rocket science. And they might not even care about the people who go into computer science. But if you can't pass this exam and you want to become a welder, good luck. These days, to be a welder, you no longer hold the torch somewhere near the metal and hope for the best. I mean, all the welding equipment nowadays is numerically controlled, and you can't operate it if you don't know basic trig. And so they are really doing this so that people have basic job opportunities. And it's the same thing in the CS courses. If you get into CS3 and you can't code a simple loop, I mean, it's just not going to happen. So these are necessary skills, and it does take a certain amount of pain. As my daughters know, I tell them the same thing about piano. All right. So, yeah, you might say it truly is not very much fun being Horstman's daughter. And they share that sentiment. So, binary search trees. So, binary search trees are a super important construct because they're, again, one of those magic data structures that manage to do something much more efficiently than one would believe that it can be done. So they have this BST property that says that for every node anywhere in the tree, that you look at all of the children to the left, they must be smaller than the node, and all of the children to the right must be larger to the node. So at first you might say, how hard can this be? You have, something like 7 here, and then you have 15 and 18 and 17 here. But wait, it's not just for the root. See, the root here, this one is smaller, and these ones are all larger. But it has to hold for every subtree, and you see the tree here violates the property because the 18 is larger than the 15. So all the nodes have to have this property. Then it's a binary search tree. So here's an example from the book, and where we use strings instead of numbers, and so this is a binary search tree for that reason. Here's one that's not a binary search tree, and let's find out why. Well, there's 2 reasons why it's not. So all of these here is less than Juliet, right? They start with A, E, and H. All of these here are larger than Juliet, but this one is not working out because it's larger than Adam. It should be on the right of Adam. So it's easy enough to fix it. You know, we could put it over here, and then we would have to put Romeo over here. And now we would again have a BST. So insertion into BST is easy because we basically follow the tree. So if it's a recursive algorithm, or the way that I'm describing it right now is a recursive algorithm. I'll come to that in a minute. So I have my tree, and I'll just pick this one here. And let's say I want to insert Fred. So, and now it's pretty clear that Fred has to go to the left. It can't go to the right of Juliet. And now I'm looking at Eve. Well, it has to go to the right of Eve because otherwise it's not a binary search tree. And now it has to go to the left of Harry, so that's where it gets inserted. That's the insertion algorithm. It's a simple algorithm. Now I've explained it to you in a recursive way. You could also look at it as an iterative way where you start at the root and then you set some pointer either to the left or to the right. And that would be an equivalent way of thinking about it. So, yeah, we have time. So, see that everyone got that. And that's all I'm getting. All right, so we have an overwhelming answer for 3. That better be the right answer. So insert an F, insert an R, insert an E, insert a D. Yep. All right, so that seems pretty clear then. And the implementation is very straightforward here. So I have add node, And so it's a recursive call on the node, right? It's a method of node, and over here I call it on the left child, and over here I call it on the right child. It's a little uglified by the fact that I have to deal with nulls, but I mean, it's simple enough. So what happens if I insert a node twice? Then it doesn't get inserted again, right? Because you see that there's two branches here, if it's less or if it's greater. So what I'm implementing here is a set. A tree set, for that matter. I mean, you've already seen tree sets. So that's insertion. And so now once we have built up this tree through a sequence of insertions, we can think about what does it take to find an element in such a binary search tree. And that again is a super simple recursive algorithm. We start at the root. Let's say we have the tree over here and I want to find Harry. So I start at the root, and that's not it. If it was, I would be done, but that's not it. So I have to go clearly to the left subtree because Harry is less than Julia. So I look at the root of this subtree, that's Eve. Well, that's not Harry, so I have to go to the right now because Harry is bigger. And so I look at this subtree, and there I found Harry. So it's, in a way, you can think of it, it's just like binary search. You start in the middle, and you either go to the left or the right, and then eventually you're done. Now, when are you done? If the tree is fully balanced, if it's always true that the left and the right-hand sides of every subtree have the same number of nodes, then in each step you cut the problem in half. So for a balanced tree with n nodes, finding an element is O of log n. And that's good, right? That is better than finding an element in an array. How about a hash table? Is it better or worse than a hash table? When a hash table finding is O of 1, because the hash code gives you the bucket, and then we assume the bucket is short. But there's a big difference between the hash table and the binary tree. If we could just assure that the tree is balanced, and grant me that for a minute, I'll talk about that later, then it is guaranteed O of log n. Whereas with the hash table, there's all these imponderables. Maybe the hash function was bad. Maybe I have an unhappy chain of a bucket chain that just happens to be very long. Maybe someone attacked my hash tree and put lots of things into one bucket. So that you don't have that warm and fuzzy guarantee with the hash table, and you do have a good guarantee with the trees. And so in practical applications, there's sometimes reasons you want that guarantee, and then the tree structure is preferred. The other reason is sometimes it's just harder to come up with a hash function. All right. So now another kind of softball question here. So I inserted 1,000 random integers into a binary search tree, and how many comparisons are needed to find whether 42 is among them? Yeah?
So if I was, let's say, a large corporation dealing with a lot of, big N, wouldn't I just account for those improbables and then choose a hash over a tree?
Yeah, in general, if hashing can be reasonably done, hashing is a little better. If you also need to visit the elements in sorted order, which sometimes happens, then the tree is better. And so we previously, in chapter 15, there was like a decision matrix. When do you use a hash table? When do you use a hash map? When do you use a tree map? And yeah. So, for example, in the C++ standard library, for the longest time, the only implementation of hash tables was, no, of maps, I should say, was with a tree, because they wanted to guarantee the performance. And then eventually they added on a hash implementation as well, because the performance is just often better. All right, so let's see. Now we have 87 votes. All right, so there's a good number of people who chose 500. Don't know why. So I have my tree. Something is at the root. It has 1,000 elements in it. So it's balanced, so we're going to assume that there's about 500 to the left and about 500 to the right. And, you know, there's a good chance that we're going to have to look in the left subtree. So that's one comparison. Then over here, now it's going to break into two trees of about size 250. And, you know, one of the two will be there. And then that gets broken down into 125, 63, 32, 16, 4, 2, and so on. So in each time, it gets cut in half. And so totally, it's log 2 of 1,000, you know, which is about the same as log 2 of 1,024, and that's 10. So there's about 10 comparisons that you need to make. And, you know, that's pretty good. All right, so also I should say that the same reasoning holds for insertion. I didn't say that on the slides, because to insert is basically to find, and then when you fail, to insert into one of the children. And so that's also O of log n for the same reason. So we have O of n log n insertion and finding. And now it comes to removal. So with removal, there are three possible cases to consider. And if any of you have actually looked at the implementation, in the implementation there are two cases to consider, because two of them will collapse into one. But let's first of all look at just the pictures. So the easy case is when you remove a childless element, because you can simply remove it. It's gone. So here I have an element with no children. If that's the one that's now unwanted, I remove it, and what I'm left over with is still a binary search tree. The next more complex case is if I have a element with just one child. So where either the right child or the left child is known. In that case, I can say, well, if I need to remove this one here, I'll just take whatever the child is, which might itself have children, right? It could be the root of a subtree. Then I'll just take that whole subtree and make that the child of this parent. And why is it still a binary search tree? Well, we need to make sure that everything in this tree is larger than the parent in this picture here. And it is, because before it was already larger than the parent. Yes?
So if that child has children,
Yes?
change the pointer to this one.
Yes, so all you do is you change this pointer, the one that's here, the dotted line, and you leave everything else alone. Because those other pointers, they form a perfectly nice tree. So I can give an example. Paper? No. No. And let's say now I want to remove 50. Then I would remove the 50 and just go like that. That's the only change I make. So the result is still a binary search tree because all of the stuff here is greater than 40. So that's the one-child situation. And it gets more complicated with two children. So here I have a node that needs to be removed, and it has the child here and the child there. And now the easiest way of doing this, and this is the standard approach, is to say, well, obviously I can't just remove it and do something to its parent, because then the parent would have 3 children, and that wouldn't work. But actually hold that thought. You'll see in 146 there are some trees that work just like that, where they're allowed to have 2 or 3 children. And then at some point, of course, when they get more than 3, then they have to be split up again. But these binary trees, they can't do this. So we have to come up with another idea. And so we want to find something simple where we still have a binary search tree. And that means we want to make sure that everything to the right still stays larger than what we're now going to put in here. And so there's only one way of doing that, and that is to pick the smallest element from here and move it up. And now, as it happens, beautifully enough, the smallest element that you have in a subtree never has a right child. Never has a left child. The smallest element of a tree, so if you have any old tree, the smallest element is obtained by going left, 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 until you can't go left anymore. So it might have a right child, but it never has a left child. So now I'm going to, first of all, copy the smallest value into the node to be removed. That way, the node value has been obliterated. It's no longer there. Now, of course, that value occurs twice, where I had it before and where I just copied it into. So I now need to remove this one here. And that removal is made easy by the fact that it has no left child, so I can use the exact same trick again from before. I just route what used to be its left, so what used to be its right child, I make that become the new left child. And that's that. So that's the most complex case. And do I have an example? I'm going to make you do an example. Yeah, so try this out. And here you have to remove C. Notice that C has 2 children, so you get to try this out. Okay, so most people think it's 3, and some people think it's... All right, so we're going to remove C, and what I just said is we're going to take the smallest child of the right subtree, smallest child is all the way to the left, and we copy that in here. And so that means we're going to have, oops, now what happened? So that means we're going to have A on top, no, D on top, because we just copied. We're leaving the left child alone, and something happens on the right subtree. So we have certainly now eliminated option A. And now we're going to do what with this thing here? It has no children, so normally we're supposed to reroute like this. There's nothing there, so all we do is we have the K left over, and that is option 3. Now, how efficient is it? So you again have to, find the node to be removed, and that's O of log n. And then the other expensive part is to find the smallest child in the right subtree. In the one case that you need that, that's also O of log n. Assuming, of course, the tree is balanced. So, and that's a big assumption, because it can easily happen that the tree is unbalanced. So, for example, if your original data was already sorted, and now you insert it into a binary search tree, then that would be bad, because you start with a 1, and then the 2, and then the 3 would have to go here. And then your binary search tree, I guess it's a tree, but it awfully looks like a linked list. And in this case here, then the performance would really be O of n, and that's a bad case. So you could try to scramble your data first before you insert it or some such thing. But more importantly, you're going to be learning in 146 there are better tree structures that keep themselves balanced. So in those tree structures, they make it so that they kind of keep track of, in some way, of how unbalanced the tree is. And if it gets too much out of whack, then they work harder on reorganizing the tree. And so there is a whole bunch of different, very ingenious ways of doing that, and you're going to learn all about that in 146. So as a practical point of view, assuming that someone has learned that 146 material and implemented that, one can assume that these trees are balanced. In the Java library, they use what's called a red-black tree. And you can actually read about a red-black tree in the textbook. It's not super difficult. And so you could just read it anytime you feel like it over Christmas break or something. And you would see that you can guarantee the balancedness. And then those log n estimates are really ironclad guarantees. So that's important. So, and so this, I guess, goes to what the question that we just had. So let's see what you think. Sorry, some of these answers must be bogus. Oh, and four is, I messed it up. 4 is compared to then a hash code. All right, so this time I don't think there's a right answer, because the answer really is it depends. You know, if you have a good hash function, a hash table is great. Like for strings, you know, there's no good reason not to choose a hash table, except if you want to iterate in sorted order. In that case, you would want to choose the tree map, just for the iteration. You know, if you're not so sure, then the binary tree is better. And actually, the hash table operation, the hash table in Java, the implementation in Java 8 of the hash table does the following. If some buckets get to be too large, then the hash table smells a rat and turns those buckets into binary trees. So they found that in some cases, people generally prefer a hash table because it performs a little better, but sometimes, for whatever reason, you get some buckets that get crazy large. And these are very large data sets, so people do this with, you know, 2 to the 30 data or so. I mean, it gets very full. In fact, more than that, at some point, I think in Java 7, they had to add another method to the hash table class. There's a size method, but size is an int, so it can only be 2 to the 32, and people were putting more than that into a hash table. So some of these hash tables are huge, and so now what it does is, if the buckets get large, then they turn them into trees. So they follow, they're worried about that case. Now, 3 and 4 are interesting. What is easier to do? Is it easier to do a hash code, or is it easier to do a comparator? And so let's see, the slight majority thinks it's easier to do a hash code. And I think that's true, because comparing things, it really depends what you have. Comparing strings, no, easy. Comparing like employee objects, probably easy by their ID. Comparing, you know, say you want to build a cache or something, you can probably compare by timestamp and some secondary thing. But let's say for whatever reason you have a large number of triangles, you're breaking up whatever, and you want to render a dinosaur and break it up into 200 million triangles. And how are you going to compare 2 triangles? You have to compare them so that one of them, that's a total ordering, so you can't just use area. There's a whole bunch of triangles that will have the same area that are quite different from each other. It can be done. You can first compare the first point and then the second and then the third. But, you know, what does it mean for the first point? Is this the first one? Is this the first one? Is this the first one? So that sounds like a can of worms. Whereas to come up with a hash code for triangles, you know, no big deal. You hash the first point, you hash the second point, you hash the third point, and you combine the 3. So it's usually easy to come up with a hash function, but it's not always clear to know whether it's any good. And so it really depends. There's no one rule to say which one is the best. And so whatever answer you picked, you can pat yourself on the back. You were certainly right for some data. That's why there's no universal data structure for you to use. They give you the choices. Yes?
How do you test your hash function?
What's that? How do you? There's really no wonderful answer, right? You have to randomly generate, hopefully representative samples. I mean, we know from experience that if you do the normal thing for normal kinds of things, that you just combine the hash values of the strings and numbers that are in your object, it's usually good. But if there apparently are these cases when data were not as random as they thought. For example, let's say you want to order you have a bunch of things with timestamps, and a lot of the timestamps end up being very close to each other, or the same. And that might happen. The hash function itself might be perfectly good, but you just happen to have lots of identical objects. So that may happen. Then, does the binary tree necessarily help you? It's just different. You'd have to try it, but. So, of course, you don't have to fret about that for the exam. So what do you need to know about these things for the exam? You should have a basic understanding of how insertion and removal works. And now, truth be told, I can never remember how removal works, which is why I made myself write a book about it. So the way to learn this really is insertion is easy enough. You just take out a sheet of paper, and there's nothing that you could do wrong. Removal, you just have to remember that there are these three situations, and they're easy enough to rediscover. As long as you know that, draw yourself an example with removing a childless element, one with one child and one with two children. The one with one child is simple enough. You remove that thing, and then you have this other tree left over, and you stick it in there. That's pretty natural. The one with the two children, you have to know the trick of finding the leftmost element. That's a super useful trick to know anyway, and you will need it for that homework 15C, so it shouldn't be too unreasonable. So that's all that we have about binary search trees. You're going to see much, much more about that in 146. So there's no class on Wednesday. And someone remind me to change the due date of the quiz. I mean, you might as well just do the quiz by next Monday. In fact, if it still have it, I'll do it right now. And so then there's the last class of the semester on Monday. Because I am going to the dentist tomorrow, and the dentist said I will probably not be up to talking on Wednesday. No, that's not C. C is not to have recursion, right?
Oh, okay. So, but then for C, you need an iterator, right? Like an iterator object.
That's the whole point of C, to create an iterator.
Oh, I didn't create an iterator here.
Oh, you need to do that. That's the.
But it works.
That is the iterator. Okay, that is the iterator.
Oh, I mean, I didn't create like inside the iterator class. I didn't create an iterator.
No. You implemented an iterator.
Okay.
So don't knock it.